Welcome back to our lecture series on nanostructural materials, science and technology. I am Professor Ashutosh Tiwari from the Department of Material Science and Engineering at the University of Utah. In the last lecture, we explored how scaling laws affect electrical systems, examining resistance, capacitance, current flow, and even the challenges of electromigration in miniaturized devices. Today in lecture 4, we shift our focus to scaling laws in optics and heat transfer. We will see how light interacts differently at small scales and how thermal transport behaves in nanoscale systems. Why does scaling in optics matter? There are two big reasons. First, optics helps in how we see small systems. Microscopes, optical sensors, and imaging setup let us probe tiny features, measure motion, and read out signals from micro and nanoscale devices. As the things we study get smaller, our optical tools and the way their performance scales become critical. Second, optics helps in how we make small systems. In photolithography, we project patterns of light onto photosensitive materials, develop those patterns, and use them to etch or deposit structures. The smaller we want the features, the more carefully we have to think about the optics behind that patterning step. So, optics both reveal the nanoscale and help build it. In the next slides, we will connect these ideas to practical limits, how optical performance scales, and what that means for fabrication and measurement at ever smaller sizes. Now that we have seen why scaling in optics matters, let us focus on one of the most fundamental effects, diffraction. When light of wavelength lambda encounters an aperture or an object of size d, it doesn't just pass straight through it, it spreads out. The diffraction angle theta is approximately equal to lambda divided by d. This means diffraction is inversely proportional to aperture size. If d is much larger than lambda, diffraction is minimal and the light continues almost straight. But when d is on the order of lambda, diffraction becomes strong. The light spreads widely. In microscopy, this effect is critical. The ability of a lens to capture diffracted light directly determines how much fine detail we can resolve. The more diffracted light we capture, the better the image detail. This is why diffraction sets a fundamental limit to optical resolution. Now that we have seen how diffraction limits resolution in optics, let us connect it to one of the most important applications, photolithography, the backbone of semiconductor manufacturing. In photolithography, diffraction sets the smallest achievable feature size we can etch using light. The characteristic dimension is given by the formula lambda equals 2 lambda divided by pi times Na, where lambda is the wavelength of light and Na is the numerical aperture of the lens. From this relation, two strategies become clear. First, using smaller wavelengths, such as ultraviolet or even deep UV light. This allows us to define smaller patterns, and increasing the numerical aperture improves resolution further. In practice, the process works like this. Light is focused through a lens to expose a photosensitive polymer called a photoresist. The exposed regions harden, while the unexposed polymer can be removed, leaving behind patterns at the nanoscale. For some polymers, reverse happen, which we will study in more detail later in this course. So these scaling principles explain why the industry has steadily moved from visible light to deep UV and now extreme UV lithography, each step pushing feature sizes smaller and enabling the dense integration of billions of transitions on a chip. Another critical factor that determines optical resolution is the numerical aperture or Na of a lens. Numerical aperture essentially measures the light gathering ability of the lens. A higher Na means the lens can accept light at a wider angle, creating a larger light cone. This allows it to capture more of the diffracted light, which directly improves resolution. In microscopy, this translates to brighter images and finer detail because more scattered light from small features is collected. In photolithography, the same principle applies. The smallest achievable spot size and therefore the smallest pattern we can print depends on both the wavelength of the light and the numerical aperture. This is why modern semiconductor tools use very high NA lenses in combination with short wavelength light sources, pushing resolution to its limits. Next, let us look at how focal length scales with size. The relationship is described by the lens maker's formula. 1 over the focal length equals the refractive index minus 1 multiplied by the difference of the inverse of the front and back radii of curvature. Here n is the refractive index of the lens material, which we assume stays constant, and Rf and Rb are the radii of curvature of the front and back surface of the lens. Now, if we preserve the overall shape of the lens, then both radii scale with the characteristic dimension d. That means as we shrink or enlarge the lens, its curvature scales accordingly. The scaling law that comes out of this principle is very powerful. Focal length is directly proportional to the lens size d. So when we miniaturize optical systems, focal lengths shrink proportionally, allowing compact lenses to focus at much shorter distances. Now, a quick checkpoint problem before we move on. Question is, light passes through a lens with refractive index n equal to 1.6 and radii of curvature Rf equal to 11 cm front and Rb equal to 15 cm back. What is the focal length using the lens maker's formula, which is 1 by Fl equal to n minus 1 multiplied by 1 by Rf minus 1 by Rb. Now imagine an identically proportioned lens that is 100 times larger. From our scaling result, which is focal length is proportional to d, its focal length should scale accordingly. Find out what will be the focal length of a new lens. Drop your answers in the comments or email me your calculations. Now let us turn our attention to scaling in heat transfer. The amount of thermal energy ETH needed to raise a system's temperature is directly proportional to its mass. And since mass scales with volume, we can write ETH is directly proportional to dQ. This means that larger objects require much more energy to heat up, simply because they contain more material. The same holds true for heat capacity, Q cap. Heat capacity is also proportional to volume, so Q cap is directly proportional to dQ. In other words, both the total energy needed to heat and the ability of a system to store heat scales with the cube of its characteristic dimension. Heat transfer can take place through conduction, convection, and radiation. In microsystems, conduction and convection are often the dominant modes of heat transport. When applying scaling laws, it is important to recognize that they are typically valid in two distinct size regimes. At the sub-micrometer scale, where the characteristic dimension d is less than or equal to 1 micrometer, here heat transfer is often strongly influenced by surface effects and size-dependent phenomena. For larger systems with d greater than 1 micrometer, where traditional bulk heat transfer models remain accurate. So depending on whether we are looking at nanoscale devices or larger microsystems, the scaling rules for heat transfer can behave quite differently. Now let us focus on heat conduction in solids. The fundamental equation for heat conduction is given by Fourier's law. Q conduct equals minus Kc times A times delta T divided by delta X. Here Kc is the thermal conductivity of the solid, A is the cross-sectional area through which heat flows, and delta T over delta X represents the temperature gradient. Essentially, this law tells us that the rate of heat transfer is proportional to the area and temperature difference, but inversely proportional to the length over which that temperature difference occurs. At the nanoscale, where the material is large compared to a micron, we can assume that thermal conductivity is constant throughout the solid. Under these conditions, if we express the cross-sectional area as proportional to d square and the length scale as proportional to d, we find that Q conduct is proportional to d. This means that for systems larger than 1 micron, the ability of a solid to conduct heat increases linearly with its size. In sub-micrometer size systems, thermal conductivity no longer stays constant. Instead, it scales with size, making Kc proportional to d. This happens because heat transfer at a very small scales depends strongly on molecular mechanisms such as specific heat, molecular velocity, and the mean free path of the molecules. As a result, for sub-micrometer systems, the conduction heat transfer can be expressed as Q conduct equals minus Kc times A times delta T divided by delta X. Since Kc is proportional to d and the area is proportional to d square and the length is proportional to d, we end up with Q conduct proportional to d square. So at sub-micron scales, heat conduction grows with the square of the system size. Now let us talk about how long it takes for a system to reach thermal equilibrium. The characteristic time for heat to spread throughout a material is proportional to the square of its size. This comes directly from Fourier number relation, where tau thermal equals F naught divided by alpha times d square. Since F naught is a constant of order 1, tau thermal scales as d square. This means that if we double the size of a system, the time it takes to reach thermal equilibrium increases by a factor of 4. For very large systems, heat spreads slowly, while very small systems equilibrate much faster. Now let us talk about convection, the transfer of heat by motion of fluid. Convection is governed by Newton's cooling law, which tells us that the heat transfer Q convect is equal to the heat transfer coefficient Ht multiplied by cross-sectional area A and the temperature difference delta T. Here, Ht depends on how fast the fluid is moving, but that doesn't strongly affect scaling. The main factor in scaling comes from the area, A, which increases with the square of the characteristic dimension, d. So, when we scale things up, the convecting heat transfer increases as d squared. In other words, larger systems with bigger surface area transfer more heat through convection than smaller systems. The scaling law for convection that we just discussed applies well at macro and micro scales, but it breaks down when we move into sub-micrometer size systems. At these tiny dimensions, convection is no longer governed by classical continuum fluid theory. Instead, the behavior of heat transfer is dominated by molecular interactions. Gas molecules in confined spaces collide and transfer energy in a way that resembles conduction more than convection. In other words, when we shrink down to the nanoscale, convection essentially disappears as a bulk fluid phenomena and transitions into a molecular level conductive process. To get a real practical understanding of scaling in energy, especially in context to water heaters, let us look into this numerical question. Working through it will give you insight into several important things like how much energy is required to heat water, how this relates to the unit of electricity on your bills, and how energy costs scale with size. The problem is as follows. A calorie is defined as the amount of energy needed to raise 1 gram of water by 1 degree Celsius. First, we will calculate how many calories are required to heat a small of water with specific dimensions. Then we will extend this idea to a much larger system, a hot tub, and compare how much more energy is needed. After that, we will translate this energy into cost using the price of electricity per kilowatt hour. Finally, we will see how the cost scales with the characteristic dimension of the system and what percentage savings we would do if the size of the hot tub were reduced. Great. Now we will solve this problem step by step. Let us start with part A. How many calories are required to bring the pot of water from 1 degree centigrade to boil? The pot has a diameter of 20 centimeters and the depth of 20 centimeters. This gives it a volume of about 0.00628 cubic meters. Since the density of water is 1000 kilograms per cubic meter, the mass of the water is about 6.28 kilograms or 6283 grams. Now the temperature rise is 99 degrees Celsius. Using Q equals to mc delta T, the heat required becomes about 6.22 into 10 to power 5 calories or 622 kilocalories. That is equivalent to 2.6 megajoules or about 0.72 kilowatt hours of energy. Part B. Energy to heat the same liquid through the same temperature rise scales with volume. So Q is directly proportional to dQ. The hot tub is 10 times larger in characteristic dimension than the pot. So the energy goes up as by 10 to power 3 or 1000. From part A, the pot needed 6.22 into 10 to power 5 calories. So the hot tub needs 1000 times that. So it means 6.22 into 10 to power 8 calories or 6.22 into 10 to power 5 kilocalories. Now on to part C, which is how much would this energy cost at 10 cents per kilowatt hour. From part B, we know the hot tub energy is 6.22 times 10 to the 8 calories. So to solve this problem, in step 1, convert calories to joules simply by multiplying by 4.184 joules per calories. That gives about 2.60 times 10 to the 9 joules of energy. In step 2, convert joules to kilowatt hours by dividing by 3.6 times 10 to the 6 joules per kilowatt hours. That works out to be roughly 723 kilowatt hours. Finally, multiply by the price, 723 kilowatt hours times 10 cents per kilowatt hours, which equals to about $72.30. This is a back of the envelope cost assuming ideal electric heating and no heat losses. In practice, heat losses and a smaller temperature rise would change this number, but the conversion steps are exactly what you use on a real bill. Now let us look at how the price scales with the hot tub's characteristic dimension D. The energy needed to heat a body is proportional to its mass, which at fixed density scales with its volume. For geometrically similar tubs, volume goes as D squared. With the temperature rise and the material held constant, the energy required therefore scales as dQ. Since the utility charges are based on energy consumption, the cost of heating also scales as dQ. Now let us calculate the percentage of cost saved by reducing the tub's characteristic dimension by 30%. Since the cost scales with D cubed, the new dimension is 2/3 of the original or 0.67 D. Cubing this, the cost becomes about 0.3 of the original or 30%. That means the cost of heating drops to only 30% of what it was before, giving a savings of about 70%. This concludes lecture 4, where we examined scaling laws in optics and heat transfer. We saw how diffraction and numerical aperture shape the limits of microscopy and photolithography, and how conduction and convection scale with system size, even in practical cases like boiling water in a pot versus heating a hot tub. In our next session, Lecture 5, we will turn to scaling in fluids and biology. We will explore how objects move through the air and water, why raindrops and parachutes reach a terminal velocity, and how drag and flow behavior depend on size. We will also extend these ideas to biological systems, looking at how scaling laws explain size, metabolism, and motion in living organisms. These insights connect physics directly with the natural world around us.